Okay, so now today we will discuss about the transformation of Cartesian coordinate to cylindrical coordinate. Okay, that is transformation between Cartesian and cylindrical coordinate. How will you exchange the coordinate system from one coordinate system to the other? Okay, so the diagram you can see here is your diagram. There are three axes are there. This one is your x-axis, this one is your y-axis, and this one represent the z-axis. And the this one is your a row is a point, here is a point, and this point is p based on from here, and this point is represented by x y z or rho, phi and z. So we have to in this transformation we will discuss how this coordinate point P will be represented from xyz to rho, phi and z, that is from Cartesian coordinate system to cylindrical coordinate system will represent this point P. So to start with, let us look at the figure, and from figure we can find out that this x, from figure we can write, just a minute, from figure we can write that this x, here this is your x-axis, so x is equals to rho of cos phi. How you understand that cos phi, phi is your angle, this angle phi, this angle phi, if we take the cos phi angle, you will get x by rho, so x is equals to rho cos phi. And similarly y will come as rho sine of phi, and z will come equals to z is z. Okay, and also rho will be equals to x square plus y square. Okay, and phi is tan inverse of y by x, and z equals to z again. So this is cylindrical, from cylindrical system, and this is from Cartesian coordinate system. So we have defined this three x, y and z in Cartesian coordinate first, and then in cylindrical coordinate we have already defined rho, phi and z based on the figure that is given here. You can take a moment and you can see the figure and how this comes. It's very simple. So we move to the next part. Now from figure we'll use simple, using dot product we will use by using next, after defining this x y z and rho, phi and z in different coordinate system, we will now use dot product, and we'll simply from the properties we can write ax cap a rho cap, this is equals to cos of phi, ay dot of a rho. I'm not giving caps. These are always, if it's small letter you will always use caps. So this is equal to sine of phi, and az into a rho equals to 0. Okay, and also and here and also and ax dot of a rho, this is equals to cos of rho plus pi by 2, that is equals to minus sine phi. So this equation, let me denote this a and this b. So a and b suppose are equation number 1. Okay, so now again we have ay dot of a rho, that is equals to cos phi, and az a rho, that is equals to 0. These are based on the properties and also the figure. So if this is b and this is c, so this is again b and this is c. So here a and b, sorry, you have defined it b here, no? So let us change it. So let us change it as, suppose a1 and this is a2, this is b1 and this is b2. Okay, so a and b are represented, say are together, they are equation number 1, and A1 and B1 we take as equation number 2, and A2 and B2 as our equation number 3. So next we will use, also we can write from the figure that product of AX and AZ, this equals to AY AZ, that is equals to 0. This is suppose your equation number say 4 or Roman 4. Let us write, wait, and write it at Roman 4, and AZ, product of AZ and AZ equals to 1. This is your Roman 5. So these are the 5 equations that we have. Now I have to omit it. So now we will use equation number 1, that is A and B. By using equation number 1, we will simply evaluate what is Ax cap, and this Ax cap will come as cos of phi, cos of phi A rho cap minus sine of phi A rho cap. So we will, from this equation number 1, we will evaluate Ax, and Ax will come as this. So we put this as our equation number 6. Next we will use, by using equation number 2, that is A1 and B1 and 5, previously the previous number 5 equation, we can say that we can evaluate Ay, that is equals to sine of phi A rho cap plus cos phi A rho cap. So we term this as equation number 7. Next we have AZ equals to AZ, that is our equation number 8. So up to this it's okay. So we have got 8 equations now. Now let us evaluate how these 8 equations will be used for transformation. Now using equation number 1 and equation number 5, so we will get A rho as equals to cos of phi Ax plus sine of phi Ay, and A rho, that is equals to minus sine phi Ax plus cos of phi Ay, and Az equals to Az. Okay. Now we know that in Cartesian and cylindrical coordinate system, in the both coordinate system we can represent a unit vector, or we define a vector at any position. So at any position, suppose in Cartesian coordinate system, so we write in Cartesian system we define a position vector A as Ax, I have told it before, plus Ay plus Az, and similarly in cylindrical system we can write a vector that is equal to A rho plus rho, then phi A phi plus Az is same Az. So by this term we can define these two vectors in different system. Now you note that Ax equals to Ax, right? So we can write this A rho plus A phi, small a phi, plus Az, product of unit vector Ax. We simply write from here, we can write it here, and that is equals to, we can write A rho dot Ax plus A rho, small a rho dot of Ax, we simply multiplying it here, plus Az dot of Ax, right? So that is, let us put that our equation number 9. Next, after that I am omitting it again. you can pull it back, your video, you can pull it back and go to the previous slides as per your wish. So now using 1, 4 and 9, these three equations we will use, and by using this equation we will get Ax, that is equals to A rho cos phi minus A rho sin phi. So you can calculate by yourself, you will find that this is coming. So we put this as our equation number 10. Okay, and similarly we can find out what are the values. We have already found out Ax, so now similarly we can find out Ay and Az. So I am writing the values directly, you can calculate by yourself also. So we can write Ay can be evaluated, it comes A rho sin phi plus A rho cos phi, and Az will be equal to Az. So this is your equation number 11 and this is your equation number 12, right? Okay, so now we will use these three equations using 9, 10 and 11. So that by using these three relations, the transformation vector of A can be represented in matrix form. Again we will simply represent it in matrix form, Ax, Ay and Az. This will be equals to cos of phi sin of phi 0 minus sin phi cos phi 0 and 0 0 1. Simply we are writing it in matrix forms, and the coefficient here in this side will be A rho, A phi and Az. Okay, so this is your matrix form. So from this matrix form we can write, this is your actually the transformation from here. This is actually coordinate system, Cartesian coordinate system, and this is your rectangle cylindrical coordinate system. So the inverse transformation we can also write. So let us now put the inverse transformation here. So the inverse transformation of vector A, the inverse transformation of vector A from Ax, Ay and Az to A rho, A phi, Az can be written also in matrix form. So can be written in matrix form, in matrix form. Okay, so here we can write the matrix form will be like this, just the inverse. Here we will first write A rho, just the reverse, A rho, A phi and Az. So we will write it here, it will be cos phi minus sin phi 0 sin phi cos phi 0 0 0 1, and in this side it will be Ax, Ay, Az, right? So this is the inverse matrix form. So therefore we can write the components of vector A in cylindrical coordinates. From these two we can write the components, or the component of vector A in cylindrical coordinates can be written as like this. We can define, now we will define A rho, A phi and Az. Okay, so simply we can write Az, we will define Az, it will be same as that of, and so Ax will be Ax cos phi plus Ay sin phi, and this is equals to minus Ax from the matrix itself, A sin phi plus Ay cos phi. So this is your actual transformation. So you can say that you have transformed from Ax, Ay, Az. So this is your position vector Ax, Ay, Az, and from here you have to come to A rho, A phi, Az. So you have to simply find out the values of a row, a row, a phi and az. So this you can see, this is your expression for a row, expression for a phi, and expression for az. So by this way, this full this is the analysis by which we can transform one coordinate from one coordinate system to other. Now your job was to, this is your assignment, is to find out from Cartesian. We have already discussed it between Cartesian to cylindrical. You have to find out from Cartesian to spherical coordinate system. Next we will discuss a problem, or we will give you example problem, what kind of questions usually comes in the examinations, right? This is your problem, one problem related to the transformation of Cartesian coordinate and cylindrical coordinate that we just discussed. What this problem states, that it has given a vector b defined by this zax plus 1 minus ax ay plus y by x az. This vector b, this is the vector b that they have provided, and they asked transform this vector into cylindrical coordinate. As you can see here, the spherical spatial coordinates are x, y and z. So you can very easily understand this is in Cartesian coordinate system. Now your job is to transform this vector b into a cylindrical coordinate system, that is in terms of rho, phi and z. Let us now see how to do this kind of problems. Now to transform, as we have discussed previously, we have discussed that we represented this in form of a matrix, and what the matrix says, we will simply define this in terms of that matrix, b rho, b phi and bz first. Okay, so we'll simply define this vector into a matrix. So previously it was the formula was, the matrix was like this, that we have just discussed: cos phi minus sin phi 0, and here it is sin phi cos phi 0 and 0 0 1, and in this side you will get bx, by and bz. So this is the matrix form of cylindrical system to Cartesian coordinate system. So now we'll simply put the values here. So we'll simply get here, by putting the values, we will get cos of phi, that is cos phi is here cos phi, and minus sin phi is minus sin phi 0, sin phi this will be same, so cos phi and 0 0 0 1, and in place of bx, by, bz we will write the coefficients, that is here z is the coefficient of ax, and for ay it is 1 minus x, and for z it is y by x, and simply represented this in this form. So therefore we can find out the values of b rho. This b rho will be equals to z. From matrix we can very easily calculate cos phi plus 1 minus x of sin phi, right? And b phi is equals to minus z of sin phi plus 1 minus of x cos phi, and bz, this is equals to y by x, as simple as that. Okay, up to this is okay. Now after that, now we need to find out the vector b in terms of spherical coordinate system. So vector b in terms of spherical coordinate system can be written as, by simple definition, b rho a rho plus b phi a phi plus bz az, like this. So vector can be represented in case of cylindrical coordinate like this. So therefore b will be equals to, we'll simply put the values of b rho, b phi and bz which we have evaluated previously. So b vectors is equals to z of cos phi plus 1 minus of x sin phi a rho, okay, plus minus z of sine phi plus 1 minus of x cos phi and a phi plus y by x az, right? So simply put the values of b rho, b phi and bz, so the expression comes like this. Also we know x equal to rho cos phi. Remember the previous diagram which we have shown, that the values of x, from there we can find out the values of x, y and z. So x there was rho cos phi and y equal to rho sin phi and z equals to z. So we simply put these values in these previous expressions. So therefore b vectors will come as z cos of phi plus 1 minus rho cos of phi sin phi a rho, okay, plus minus z sin phi plus 1 minus rho cos phi, okay, a phi plus tan phi az. So this is your final y by x is equals to tan phi. So this is your simple answer. So you can find out, so you can simply tell from the term, as the problem said, this vector, it was in previously in Cartesian coordinate system. So if we transform it into a cylindrical coordinate system, so vector b will be represented by this, and this is your answer. Okay.